So let us look at what are these refinable parameters we are talking about in a profile. So let me do one small my specialist diagram and draw a profile. Oh, it's not looking very bad, but it is a very bad diffractometer on which this profile has been obtained, but it's okay, we can discuss that. So we have a profile, and this profile has to be fitted now. So it has a certain x direction gives us the 2 theta value, the y direction gives you the intensity. So the x value we read out, and it could be 1 peak, it could be 2 peaks, it could be 3 peaks. So what are all the refinable parameters which will fit this particular shape of our profile? One of course is the structural parameter, which we don't have, we don't know the structure, so we will not touch it. So we will keep it separately, but those are refinable, remember. If we know the structure, if we know the positions of the atoms, then these are also refinable parameters in the way we discussed in the case of a single crystal analysis, the so called refinement procedure. The profile parameters can be separated out from the structure parameters, and those are the 2 theta 0, which is specific to the instrument. Sometimes the instrument alignment is such that there is a little deviation from what we call as 2 theta 0. So that has to be, normally it can be estimated, or the instrument people will give us that particular value. It can also be ideally determined by collecting a standard data. For example, if you put silicon and you have to get a reflection at 2 theta 28.65 if the 2 theta is at 0. So you put silicon on the machine and find out where the peak is coming, and that will give you the 2 theta 0. If it is coming at 28.6, then you know there is a 2 theta shift of 0.05 in the negative direction. So that correction has to be applied. So and it also is a refinable parameter. We can vary it with respect to the length, the extent to which we carry out the structure determination in using 2 theta, the profile refinement using 2 theta. Then there is a typical instrument for profile. One of them is caused by me just now. So it can have a shape throughout like this. This is an issue which can be corrected. Then profile asymmetry, which is very obvious in this profile which I have drawn. Then if you now consider the powder pattern to be going from a certain 2 theta value to certain other 2 theta value. So let me extend it like that. Then there is a background which goes like that. So the background which is going like that need not be a straight line. It can be falling off with respect to sin theta. It may be a first order function, a second order function. So we have a polynomial which takes care of fitting the background. So we can now use those as the refinable parameters, refine the functions of the polynomial to account for the background, and this is a very important factor. How you account for the background now will tell you how accurately you can get the peak positions and their intensities. Suppose you put the background way up here, then you lost all the reflections. So essentially background selection is a very crucial factor, and the way it is done is to choose the background along the 2 theta directions, starting from one of the low angle regions to the highest one, and choose some 20 or so points which are definitely not coming under any peak indication. Even if there is a little kick here, we do not take it as a background point. So those background points now are fitted with a polynomial, so that the peaks and the peak positions stand out. And so this is a little tricky issue, but again these are refinable. So profile refinements will handle this kind of a phenomena. Then of course crystallized size and micro strain, and this once we have the profile parameters analyzed, we can look into those issues. Specimen profile breadth parameters, this is due to the nature of the specimen itself. As I mentioned in the beginning, the choice of the sample preparation. So if there is no such preparation done, somebody throws the powder on the diffractometer. Each powder particle, if you can call it as a particle, will have different sizes. So the size of the grain will be different, and if different size grains are there, it will also introduce a certain breadth associated with the peak. So the peak become wider. It is nothing to do with the fact that it has the size effect. It is because each crystal has a different size. So, if you have the sieve experiment which we discussed yesterday, then it is possible to look at the sieve experiment and then get uniform sized particles, and then it will not have this difficulty of specimen profile breadth parameters. But if that does exist, we can refine them. And of course, the most important thing is the lattice parameter. See, we determine some ABC alpha beta gamma by indexing HKL peaks we identified, and we identified maybe 20, maybe 30 depending upon the quality of your diffraction data. That is probably not an indicator of the correct lattice parameters. So, lattice parameters also can be refined under the profile parameters. So, profile parameters are so many: specimen transparency, specimen displacement, these are all issues, and of course, the major thing is the absorption, because it depends upon how many heavy elements are there in your material. If there is a heavy element, particularly when you are doing a pharma analysis and your excipient is, let us say, titania, it has titanium in it, and as a consequence one has to be worried about the absorption effects. So, this absorption is also a refinable parameter, and so once we refine all these parameters, we can do the profile fit. And there are packages that are available to do both the pattern decomposition as well as the structure determination. Now, what I will do is I will take the profile refinement examples when we discuss the polymorphic issues. Here I am going to take you directly to the structure determination protocol. This is ab initio structure determination protocol. That means you have no idea of the structure, you recorded the powder, you did a pattern decomposition. Using this package called extra, the program, you can do the pattern decomposition, and this pattern decomposition is done in the following way. We consider the data from 2 theta 3 to 100.42 degrees, and on a given some particular compound we have collected the data. I think the picture of that is somewhere here. So, this green line is the powder diffraction pattern. The green line which you see here is the powder diffraction pattern of a compound. This is bismuth vanadate, and when it's a different kind of bismuth vanadate. It's not a direct bismuth vanadate, it's a substituted bismuth vanadate, a compound for which the structure was not known, and you see it's a very complicated pattern. In fact, it indexes as a triclinic system. Okay, so we have this powder pattern. So, we now want to determine the structure of that compound. How are we going to do that? What we do is we now go back and look at the 2 theta values. We take the 2 theta values from 3 to 100.42, and the data are collected at 0.02 degree intervals. That means we have a very large number of observations, and what we do here is to consider each one as an observation. So, whether it is a peak or otherwise, each measurement is now considered an observation. So, we have so many measurements that are available with respect to 2 theta. And so, these measurements now which appear here on the green line are the powder diffraction pattern of that particular compound. So, the example here which is given here is that with that we were able to isolate and identify 498 reflections. So, it is not just the peaks. If you count the number of peaks here, it is 1, 2, 3, 4, 5, 6 like that. If you count, maybe about 35 to 40 you will get. But if you do this fact that if you do this analysis of where each and every HKL can come in this crystal system, once you have indexed the pattern has been indexed, the ABC alpha beta gamma is known, so we can calculate how many reflections will come up. So, each and every reflection is assigned to the corresponding 2 theta value, and that particular 2 theta value is now considered a reflection, and the intensity is considered as a measurement. So, when we do that as an intensity measurement, then we will get the 498 reflections generated. Let me take you back here to show what I mean by that. So, if you look at this one, if you look at the count of peaks 1, 2, 3, 4, 5, 6, 7. So, in this case there were 7 peaks on the powder pattern. But if you look down here and count the number of reflections that are possible, you will see 1, 2, 3, 4, 5, 6, 7, overlapped peak 8, 9, 10, 11, 12, 13, overlap peak 14, 15, 16, 17. So, you have a very significantly larger number than what you have there. And of course, the overlap peaks will remain overlap. So, we have to do the pattern decomposition to identify individual ones, and we have done that through profile analysis. So, if we have done that exercise, we will end up getting 498 reflections. So, it is as though you have a single crystal data now which has given us 498 reflections. Then you calculate the profile R, the R factor associated with the profile. How do you do that? The R factor that is associated with the profile can be obtained in the following way. You have the powder pattern. Now, based on the idea of where the reflections should come, we have assigned the intensities. The assigned intensities will generate reflections, and those reflections are marked as plus here. So, all these are possible positions of where the intensities can come in this powder diffraction pattern. Okay. So, the points plus is therefore the I calculated, and this is the I observed. So, for every point we have a I observed and I calculated. So, what did we do in the least squares refinement in the single crystal case? We took the modulus of f of HKL minus modulus of the observed FHKL minus the calculated FHKL, the modulus, and then we made it a minimum quantity by doing the refinement protocol, and then we calculated an R factor. So, similarly we calculate an R factor here, and that R factor is now associated with the profile. So, we call it as the profile R factor. Of course, each and every measurement is now has a different advantage, because at lower angles we have more intensity, at higher angles we have less intensity. So, we need a modifying function, and that function is the weight factor. So, we attach what is known as a weight factor, and therefore, we have two R factors. The profile R factor, which is 11% here, 11.55%, which is pretty good for a powder diffraction pattern, and the weighted R profile is 15.80%. So, when we have this kind of a situation, we can believe that the 498 reflections are reasonably well generated. So, we now have a list of HKL and intensity 498. It is still not sufficient, in a single crystal, as you all know, by now you have thousands of reflections for a unit cell of a defined value. So, here we get still not that kind of numbers, but 498 reflections is not a bad idea. So, using these 498 reflections, we can either use the Patterson methods or direct methods to hope and get the positions of the atoms. So, in this particular case, luckily for us, the example which we took, in fact, this is the structure which was determined as the first ever structure in India for a ab initio measurement. And this was done in our laboratory by a person by name Digambar Porab, who is now teaches in Goa. So, this compound we know is a bismuth vanadate. Okay. So, it has two bismuth atoms and one vanadium atom according to the molecular structural formula. And using that information, we now went on to use the Patterson synthesis. So, 498 reflections, we used the Patterson method. We also used the direct method. And then in both cases, we were able to identify two bismuth atoms and one vanadium atom uniquely, because these are standing above, over and above the oxygen atoms which are present. So, once we have this information, we cross checked with using both the methods, and Patterson gave directly the two bismuths and one vanadium. We verified this by running the direct methods also, and found out the two bismuths and vanadiums are reasonably well located with a good R factor, overall R factor associated with these 498 reflections. Then what was done was to use this approach to do a difference Fourier. So, what we did was we accounted for two bismuth and vanadium and did a difference Fourier map. And this difference Fourier map, and this program that was used is a program called GSAS that was used for the refinement of the structure later. But at this moment, Patterson and direct methods gave the positions of the heavy atoms. These heavy atoms were now subjected to difference Fourier analysis. That means effectively we remove the bismuth and vanadium and see what is left in the density. And this picture which is shown here gives us the difference Fourier map. And you see the two bismuths here and the vanadiums here, the vanadium here, the bismuths there. And so, this is a three-dimensional plot of the difference Fourier, and whatever is the density which is coming up here represents now the oxygen positions. We then identified these atoms, got the oxygen positions, and put all the heavy atoms as well as the light atoms together and did a refinement. The refinement was a profile refinement, but with the structure information available, with the structural parameters put in. So, what are the structural parameters we are talking about? The structural parameters are the same as the structural parameters we always refer to, that is the position coordinates x, y, z, and then the thermal parameter, which could be isotropic B or anisotropic B11 to B23, the 6 parameters, and of course the scale factor. So, these now define our structural parameters. Okay, now here what we are doing is to put the bismuth and the oxygen positions into this one and do a refinement, and then do the difference Fourier map. And that difference Fourier map, of course, every time as we do the structural parameters, we should also refine the profile parameters. The way it is done is in fact very well organized, and that is known as the Rietveld refinement, due to a person called Rietveld. So, what we should remember, particularly when people loosely talk about Rietveld refinements in many cases, because Rietveld refinement is in the phrase itself is a refinement technique. That means you should have a starting model. The starting model in this case came from our position of the bromine, the position of vanadium, and then the difference Fourier map giving the positions of oxygens. So, we are not doing any other aspect. See, we took the powder pattern and decomposed the powder pattern and identified some 498 reflections, used the Patterson approach and the direct method approach to get to the heavy atom positions. Okay. After that, the heavy atom positions were put in and a refinement was done. So, before we could do all these things, we have done the profile refinement in the beginning. That is, we have fitted the every powder diffraction peak with a profile, and we have refined the parameters that are associated as is indicated here. So, essentially what I am trying to tell is the way in which we have to do the Rietveld refinement. It is not a structure determination protocol. Rietveld refinement will not help you to solve structures. There is a misnomer, and so I want to remove that misnomer, because Rietveld refinement is only a refinement technique, and it uses both the profile as well as the structural parameters. So, the number of parameters are many more, because you have to have 2 theta 0, you have to have instrument profile, you have to have background, you have to have lattice parameters, everything to be refined. Before that, before you introduce the structural parameters into the protocol. So, when you do this refinement, therefore, the so called Rietveld refinement, you need a starting model. The presence of the starting model can be generated the way we discussed, or the starting model can be obtained from the database. See, if you go to database, ICD database, and look at different kinds of bismuth vanadates, the data that is available on those, there is a good possibility that there may be a structure very closely related to this structure with the cell dimensions agreeing nearly the same. So, in such a situation, we can take those coordinates and put those coordinates as the structural parameters and go ahead and refine. Then it will be a successful refinement. So, in other words, Rietveld refinement can do only small changes in the starting model. It cannot determine a structure, find the position of an atom in space and so on. And so, so the refinement technique which is used under the Rietveld protocol is essentially referred to as a toothless technique, because it can only grind it to a certain extent. It cannot grind it to a final structure refinement position, final structure refined positions of the atoms. So, keeping that in mind, it is a very extremely useful technique, because any powder diffraction pattern in principle, its structure can be determined ab initio, like the way we discussed, or we have to now find ways and means in which we can find the starting models. If we can do that, then this Rietveld refinement protocol will do a wonderful job, and we will get a good fit as is seen here. All these are the calculated positions marked as red in this particular case. So, all these marked in red as plus are the calculated positions, the values of the intensities I calculated. I observed is from this, and then you see the pink display here telling how well it is the fit. So, we can calculate the corresponding R factors, and this is a fairly successfully determined structure. So, the structure is shown here. It is not a simple structure, it is a fairly complex structure. This is the biggest structure of in those days determined by ab initio structures. Of course, there was a structure of a zeolite which was determined around the same year by Lynn McCusker, and that is a much bigger structure and a much more challenging structure. But this is one of the bigger structures which came from our laboratory. So, this is the structure of bismuth vanadate. The positions of the atoms are very clearly seen here. It is as though it is a single crystal structure. All the details associated with the single crystal structure can be derived from this.